Okay, so first of all, I'd like to thank the organizers for inviting me to speak here, my old hunting ground where I trained many years ago. And I didn't bring the good weather, you're right, but I actually had to like the rain. I'm missing it in San Diego. It's too dry there by half, you know. So anyway, so I'm going to talk about something a little bit different now, and that is, so the focus of my lab is to understand how we'll basically work on blood vessels in the brain, and we're particularly interested in how stimuli such as hypoxia and inflammation change blood vessel properties, drive cerebral angiogenesis, and change blood-brain barrier integrity. And I haven't had a lot of discussion here so far about blood-brain barrier integrity, which is surprising, I guess. But anyway, so let me get into the slides. So our model system, by the way, is we put mice in a hypoxia chamber. We reduce the oxygen level to 8% oxygen, which is quite a bit lower than the 21% we're breathing at sea level. And where's the pointer gone? The pointer go?
Inside the computer, the pointer.
Yeah, the slide computer. To the back.
Here.
Oh.
That's what you want.
Okay, that's fine. Thanks. That's okay. So, how does it work? You just press the red thing? Is that
Yes.
right? Oh, gotcha. Okay, thanks for that. Oh, really good. Yeah, so basically what happens is this panel just shows you what happens in blood vessels when you put mice in a hypoxia chamber. You get a very strong endothelial proliferation response. So CD31 is marking your endothelial cells, Ki67 is your proliferation marker. And you can see you get a lot of endothelial proliferation. And interestingly, by the way, we put these mice in these chambers for anywhere between a couple of days and 2 weeks. And what happens is, and basically, there's not much action until about two days, and you start seeing endothelial proliferation. And it peaks at around 4 days and starts to wane, and that's shown in this panel here. And not surprisingly then, this angiogenic response culminates in a big increased vessel density. This is a CD31 stain, the old-fashioned DAB staining. But actually, over 2 weeks, you get up to 50% increase in vessel density. So this is no small thing. These blood vessels are really regenerating, and there's every reason to think that probably happen in human brains if we expose ourselves to the same stimulus. And so basically, I guess that what tells you then is that basically the brain's got an inherent capacity to respond to this hypoxic stimulus, to mount an angiogenic response, which therefore brings each neuron closer to a source of oxygen. So like in many things in life, to every upside, there's a downside. And the downside is that there's quite a bit of transient blood-brain barrier breakdown. So under pneumoxic conditions here, you can see there is no BBB breakdown. We're using fibrinogen, extravascular leak as a marker. But under hypoxic conditions, you see quite a bit of fibrinogen. And I'll put out this graph on the right, and that's showing that with days in hypoxia, the number of vascular leaks increases from day 4 to day 7. But by day 14, it's actually gone down. That suggests that there's an endogenous vascular repair mechanism. If there wasn't one of those, then basically the number would just keep escalating up. And so clearly we're interested in about what cell types, how do they change in response to this vascular leak. And we're particularly struck by the response of microglia, because microglia will go in, they'll aggregate, they'll migrate towards this vascular leak, and they really accumulate hard, and they appear to be more activated. And that's shown by this typical morphology down here, typical ramified under pneumoxic conditions, changed into a very much amoeboid morphology under hypoxia around the vascular leaks. Now, this raises the question, well, are these microglia doing a good thing or a bad thing? So it's very simple to test that. You simply remove them all by our good old friend PLX5622. So 7 days treatment of PLX removes greater than 90% of the microglia in all regions of the brain. And when we do that, you can see from this panel here then, this is a typical sort of, these are hypoxic mice that haven't received any PLX. When you hit them with PLX, you see more leaks, and the leaks are worse. And that happens in all regions of the brain. So what that's telling you then is really that microglia are playing an important vascular protective role, because when you take them away, hey presto, you get a lot more leak. Oh, okay, 20 presses. So as well as getting more vascular leak, basically we also see two things that are critical to the blood-brain barrier. First of all, we see a loss of tight junction proteins when mice are treated with PLX. So that means that the actual, ZO1, occludin, claudin-5 are lost in the endothelial junctions. That's quantified here, occludin and ZO1. And we're also seeing a loss of astrocyte end feet, and that's quantified by looking at aquaporin 4. So just to briefly sum up this first part then. So chronic mild hypoxia induces a transient vascular leak in several blood vessels, but it's associated with microglial accumulation and activation around those vascular leaks. It's very much a regional, it happens in all regions of the brain, but it's particularly strong in certain areas, and that's the olfactory bulb and the midbrain. And we wonder why that might be the case, and we think, well, maybe the olfactory bulb is a sort of constant regenerative site, even in the adult, in the sense that there's always an ongoing neurogenesis. The rostral migratory stream brings down all these new neurons. And what happens in the midbrain is a bit of a mystery, but it could be that hypoxia could be some kind of predisposing factor to opening up those blood vessels to predispose into some diseases such as Parkinson's and such like. I've shown you that microglia depletion increases the vascular leak, and it's associated with loss of tight junction proteins and loss of vascular uncoupling. So it's pretty suggestive that microglia is playing a vascular protective role. So far, so good. And then, quite a few studies have shown that, or suggested that blood-brain barrier integrity declines with age. So is this important, and what's happening with microglia? So basically, we could test it very easier by comparing the responses of 2-month-old mice or 20-month-old mice, so young and aged mice, to the hypoxic response. And you can see that in the pneumoxic conditions, there's no vascular leak. In the young mice, we're seeing 1 or 2 leaks in the olfactory bulb and the midbrain. But you can see in the aged mice, we're seeing a whole lot more leaks. And that's quantified down this panel here. And this, by the way, occurs in all regions of the brain. And it's not just a sort of a small thing. This is like a 5 or 10-fold increase in vascular leak. So these blood vessels are much more vulnerable to breakdown. This is even evident when my postdoc was sectioning by the cryostat. You really don't see any hemorrhaging. Well, you've got to look very close to see any hemorrhaging in the young. But in the aged, you can see a lot of vascular leak there in the olfactory bulb, and some occurring in the midbrain. And like I showed you in the young, the number of vascular leaks is also going down, both in the young and the aged. So that's also important to bear in mind. So back to microglia then. I've shown that microglia cluster around these vascular leaks. They seem to be active. What are they doing? We've shown they seem to be protecting. But, what about the activation state? So just crudely, looking at a MAC1 stain, first of all, we can see that we just compare under pneumoxic conditions. Microglia are pretty ramified in the young brain, but in the aged brain, they're much more amoeboid and much more hypertrophic cell body, shorter processes. But what's interesting what happens in the hypoxia is that the young microglia don't really change so much. There isn't that much difference going on. But the aged microglia really change a lot. So in other words, aged microglia are both more activated in the pneumoxic resting state, and they're even more activated when you put them in hypoxia. So they're super responsive. This is also, if we look at other markers of, say, Ki67, we see very little Ki67 or microglial proliferation in the young brain, but in the aged brain, there's a lot of proliferation going on, and that's characterized here. We also looked at another marker, CD68, that also is much lower in the young than the aged brain, and in a similar manner to MAC1, while hypoxia doesn't have a lot of impact on the CD68 number in the young brain, in the aged brain, it really does crank up. You can see that here. So far, it looks like, okay, there's more vascular leak in the aged brain, and the microglia are more activated in the aged brain. So you might think, okay, there's going to be better. So what's going on? It seems like a paradox. And so what we did was look at a correlation then between extravascular leak, shown in fibrinogen, and the microglial accumulation or aggregation in CD68. And what we saw then was basically a very tight correlation in the young brain. But when you get to the aged brain, there is a little bit of correlation, but there's actually a lot of vascular leaks. There's really nothing going on. There isn't any microglia. You're just staying out there and staying very non-responsive. And that's quantified in this panel here, just showing there's a really marked reduction in these microglia to go around the vascular leaks in these aged brains. What's going on here? You know what? I think it's just overshot by 1 or 2. Yeah. Let's just make sure. Oh, yeah. Okay. Now it's kind of like, all right. Too many presses, right? First of all, it won't move, then it moves a few, then it. Okay. Let's see if it comes back to life. Well, okay.
I think we'll just
I can tell you. I'll do what my colleague did earlier on, just carry on chatting. So basically what happens, so the question is, okay, so we're seeing less vascular protection in the aged brain. So is that because the microglia sort of switched from vascular protective to vascular destructive? And so to test that idea, we just hit the mice with PLX, the aged mice, and that actually showed us then that there still is a very strong vascular protective response in the aged brain. In other words, if you remove the microglia, you get a lot more vascular leaks, even in the aged brain. Is that a new situation I've created? Oh, there we go. You got it back. Well done. All right, listen. We'll go forward a little bit. There we go. Yeah, and that's shown here. Oh, if I just shot again. Ah, come on. I'm having fun with it. Okay. Right. So, so this interesting situation, more leaks in the aged brain, and yet paradoxically less vascular protection, although the microglia are more activated. So it raises the question, well, if we sort of use the old tried and tested approach of using minocycline to attenuate microglial activation, would that take the microglial phenotype back to that of a younger microglia, or microglia in the young brain? So we treat it with minocycline, we see very much a strong diminution of the MAC1, strong CD68 suppression, and less proliferation of microglia. And yes, it's true. So the number of vascular leaks is definitely reduced in the minocycline. So it seems as though, I'm rather heavy-handed. I'm not handed at all. Oh, man. I think Marina said it, but I think I've got it even more than Marina, I think. Okay. So just to summarize the second part then. So bottom line is, aged brain leak a lot more in response to hypoxia. There's a lot more vascular leak. It's telling you that the blood vessels in the brain, in the aged brain, are much more vulnerable to hypoxia. So the microglia are more activated in the aged brain, but paradoxically, they really don't do their job. Then they basically are associated with a lot less reduced vascular protection. And the depletion studies show that they're still playing an important role, but perhaps attenuation of microglia back into a sort of more of a young phenotype may be a good thing. So in summary then, basically what this is, I guess the point I'm going to make here is that hypoxia is more common as we get older. I mean, we get hypoxia when we're young too. I mean, people have asthma, they have sleep apnea, let's not forget COVID. So hypoxia is a common part of our lives in many disease conditions. And as we get older, it becomes more common. So disease like lung disease, COPD, cardiac failure, and also cerebrovascular insufficiency. So hypoxia is a fairly common factor. And so what I would argue then is that basically hypoxia is going to lead to blood-brain barrier breakdown, which is going to lead to a sort of disruption of the cerebral homeostasis, which could lead to neuronal dysfunction, neurodegeneration, and perhaps cognitive decline. And I haven't got it here, but we've shown recently that in the novel object recognition test, we put aged mice into a chamber, we basically test them before and after, and we have control mice, and they really do take a hit in terms of novel object recognition. And interestingly, when we bring them back to the pneumoxia conditions, they don't recover. So we test them a week or 2 weeks after, they simply don't recover. So it looks as though whatever pathology is happening in response to hypoxia has long-term sequelae. So that's important to bear that one in mind. And I'll just leave with the idea then that basically, perhaps in the aged brain, they're just too activated. So if we can somehow, titrate back the aged microglia into a younger phenotype, that could be productive. And so I just want to acknowledge the people who did the work, and that's Seabok Holder and Arjun Slapkota. And obviously thank the guys who paid for all this, the National Institute of Health, the National Multiple Sclerosis Society, and many years ago, the Wellcome Trust. So thanks for your attention, and I apologize for the technical up and down and left and right, but I'll take any questions.
Questions, please. Thank you very much, Richard.
Who we got?
Carl, just you.
Thank you. Really interesting work. I'm just kind of wondering about the molecular mechanisms and if you see any sort of differences in terms of HIF, PHD pathways between young and aged mice, and that could be responsible for changes in hypoxia sensing and things like that.
So the only thing I can tell you about molecular mechanisms is in the original paper we described using a fibrinogen peptide. So we use fibrinogen as a marker of extravascular leak. But catrinate acid glue up in the UCSF has shown that fibrinogen leak out can stimulate microglia into an angry, activated morphology and start attacking myelin as in an EE model. And so we thought, well, we'll try the same peptide and see if it's also going to block our, the fibrinogen MAC1 interaction. And it did exactly that. It blocked the microglial accumulation, and it also led to more vascular leak. I should say that, about a year ago, we got some fibrinogen knockout mice, and it's been slow to get them going and everything, but essentially, we're seeing a very similar thing. So fibrinogen knockout mice are showing very marked defect, not just in aggregation, but even in terms of general activation of microglia. So they're not responding the same. They're simply not getting activated. They're not proliferating. They're not showing CD68. So we think that the fibrinogen sort of MAC1 interaction is something important. But, I mean, that's just the sort of endpoints. You're talking about the HIFs, and so I haven't actually looked at that per se. I know Joe Lamanna at Case Western has compared young and aged mice and showed there are certainly some differences. I think in VEGF certainly comes down much lower. It was much lower in aged mice. But the angiogenesis response in the young and aged mice appears very similar. It's kind of a shock, because we'd expect there to be a much, kind of slower regenerative response in aged mice, but not so. It just seems the vascular leak is very vulnerable, though. So it's like there's something happening to those aged blood vessels that isn't healthy. And I guess one of the things we're interested in is actually it's a two-way street. So here we've talked a lot about microglia and neurons communicating and shuttling factors between them. But I also think the communication between blood vessels and microglia is very important in terms of, in the aged mice, we're seeing more vascular leak. Is that because the blood vessel is just more leaky and that causes more microglial activation per se? Or is it because the microglia are more angry and they're sort of doing bad things to the blood-brain barrier? So we're sort of trying to unravel that as well by various interventions at the moment.
Brilliant. One quick question and answer, please.
Thank you for the presentation. I have two questions. The PLEX studies that you had, did you titrate what the optimal dose for PLEX was to show the effect that you showed?
No, we didn't. No, we talked to the guys at Plexicon, and we talked to Kim Green at Irvine, and we were given, I think it was a 1200 ppm and a 300 ppm, and so we didn't do that. We just went in there. I mean, one of my goals was along the way was to, okay, we've gone for a big hit, and this is pretty dramatic. But in the same way that James Rowe yesterday he briefly showed a slide about, I think, was it Hugh Perry's work, showing that some antagonists of the CSF1 receptor appear to show some protection in Alzheimer's. And in a similar way, you could argue, well, if you could hit, these mice with a low dose of PLX 5622, it wouldn't remove the microglia, but it'd probably take their activation state down, maybe analogous to the way the minocycline did. So that's something we could think about.
That was my next question. So now if you then tune them down with a minocycline, what are you hitting with that compound?
Sorry, tune down the minocycline, did you say?
Yes, you tune down the microglia is what you claim with the minocycline, but what does minocycline do to microglia? Is it specific for microglia?
It's not absolutely specific. I mean, it's in the literature, it's a well-established suppressor of microglia activation. Like a lot of others have used it, and it does also impact blood vessels. So it's not a clean drug. We know that. That's why messing around with PLX 562 and titrating might be more informative in the long run, be more tighter and cleaner.
Thank you, Richard. If you don't mind, a little question after that, yeah.